Hello and welcome to KAUST from wherever you're logging in across the internet. My name is Shihab Ahmed. I'm a professor at KAUST, and I have the pleasure of moderating today's session. Today's session will be discussing the energy and the smart grid. Energy is really at the core of every discussion on smart cities that we can think of. Energy is at the core of such discussions, and usually one of the main issues that people ponder about and think of. Energy is delivered to us through a very complex network of wires and cables and switchgear that we see all around us, but maybe we know very little about. And renewable energy integration into such a network is a challenge that we will hear more about today. Today I have the pleasure of introducing and welcoming Professor Saifur Rahman, who's a Life Fellow of the IEEE and the founding director of the Advanced Research Institute at Virginia Tech. He was also the IEEE Power and Energy Society president for 2018-2019. And in this keynote lecture, he will talk to us about how the electric utility has to evolve to make the integration of sustainable energy sources possible in Saudi Arabia. Professor Saifur Rahman, I will leave the floor for you to introduce the topic and teach us more about the topic.
Okay, Shihab, can you see my full screen now?
Yes.
Thank you very much. Shihab, thank you for the kind introduction. And for my audience, grad students, faculty, invited guests, welcome to the session today. As you can see in the title of my presentation, the three keywords I want to focus on, maybe four. One is connectivity, second is smart grid, third, integration, and fourth, renewables. These are the keywords. Why is that important? Many of us, maybe all of us, have heard the word smart grid. It's a very vague name right now. It can mean many things to many people. I'll try to bring it to your level, what it means, how can we participate in the smart grid, what are the components, and where you want to specialize. So this is where I'm starting. And then, of course, I'll talk about renewables, focusing more on solar energy, because that is a big developing option for Saudi Arabia today and globally, of course. And then what needs to be done to make renewables more practical in the electric utility network. That's how I want to move on. So having said that, let me move on to defining few things. Again, smart grid, what is it? I am doing smart grid for, I don't know, almost 14 years now, giving lectures, writing papers, all that. So this is what I believe is the reality today. It is a concept which has many elements where we monitor and control different things in the chain of generation, transmission, distribution, and end use. There's a power network: generation, transmission, distribution, and end use. That's all we do. However, what does smart grid do in this context? We have built smart grid or building a smart grid so that we can deliver this electricity more efficiently and at the lowest possible cost. That's the objective for smart grid. Now, then the question is, fine, if you understand that, the motivation therefore is, we want to make the grid, the big grid, smarter, safer, reliable, and more cost-effective. I put that in red letters. That's for me very, very important, cost-effective. We'll be using sensors, communication technologies, and distributed computing to make it happen. So notice here, I said, make the grid smarter, safer, reliable, and more cost effective. I didn't say cheap. It's not cheap. It's pretty expensive, smart grid. But it's the reason we want to invest to make it cost effective. Look at this picture. Sorry, this picture right here. I can explain this to a high school student, the difference between a smart grid and a normal grid. The phone on the right, the black phone, you probably don't know this. You're not old enough. I grew up with this kind of phone. That costs in the US maybe $10, $12, and it's fine. In fact, gives a better sound for landline calls. Pick up the phone, dial the number, and the other party picks up, you can talk. That's it. If phone means audio, right? Phone is a phone. That's fine. On the left-hand side, I have a smartphone. If you want to buy a iPhone 12 Plus, cost you more than $1,000, maybe $1,200. If you want to make only a phone call, you as well buy a $12 phone, not $1,200 phone. So why do you buy a $1,200 phone? It's still a phone. I call it iPhone. It's not a computer, it's a phone. However, that phone gives you much more service, much more functions. It can do social media, it can do camera, it can do internet, it can do word processing, it can do Facebook, all these things. That's why we don't mind spending more money to buy a phone which can do more things for us. That is the crucial difference between a normal grid, which is being used for 140 years now, generating station, transmission line, distribution substation, either building. If that's what you want to do, you don't need a smart grid. No problem. That's it. It's going on forever, 130 years, all over the world. But because of renewables, because of the diversity of load and many different things, we want to be a smarter grid. That's why we invest the money to make it so complex. But end of the day, it is safer, more reliable, and cost effective because it can do more things than otherwise possible. If we did not have in our distribution network ability to feed power from my home to the network, I would not buy PV. It don't work for me. So this is the difference. Historically, we have done one-way flow, power station to my home. Now my home is a small power station because I have rooftop solar, which is serving part of my house. That's why we need smart grid. Now, so what then are the starting and ending points of a smart grid? Where does it start? Starts at the power plant, of course. You need electricity, transmission line, distribution network, comes to your building, your home, and then your end use, your refrigerator, air conditioner, washing machine, whatever it is. That's the whole smart grid span. So I therefore say the smart grid starts at the generator and ends at the refrigerator. That's my definition. Okay. Then what then are the building blocks of a smart grid? Building blocks, what makes it smart? At the top of the pyramid, I have a technology, smart network, smart meters, smart computing, smart control systems. All of that is, you can buy all this today. No problem. You can buy them globally in Saudi Arabia as well. Next important element is standards, meaning many companies manufacture these hardware. How do you know if you buy a meter from Siemens, then you buy your controls hardware from ABB, and buy your switchgear from GE, would they work together? That's why you need standards to make sure all the vendors who build and market these devices follow some standards. So standards for smart grid has been built in the last 10 years and it's working fine. Then this very different topic now, the green box, rates and regulations. I'll talk more in a few minutes. Unless you have incentives for people to use energy in a more careful way, they would not care. They'll use energy whenever they want to. We know very well during peak hours, when it is hot summer afternoon in Saudi Arabia, the demand is very high. So power company's system is stressed to meet that demand. If somehow through some rate structure, pricing structure, we could say, if you avoid using electricity from 3 p.m. to 7 p.m. on a hot summer afternoon, we'll give you some incentive. That's an example of a regulation. That's working its way through in many countries. That's happening. At the bottom, the blue box is consumer awareness and education. If public does not know what a smart grid is, how it helps them, how they can use the different rate structure to save money, they wouldn't care. So to me, as an educator, that's a most important component. I have the responsibility, you have the responsibility to make the word clear to your parents, your family, your friends, and your colleagues that smart grid can help you. Only then they'll be willing to spend more money to make it real. That's the set of building blocks: consumer awareness, rates and regulations, standards, and technology, in that order. Fine. Having said that, let's move on. How the grid has evolved over the last maybe 15 years or so, roughly. On the first third of the screen, I say before smart grid, and bottom half after smart grid. Before smart grid was there, we have been living with this for 100 years now. You had a power plant and many power plants, a step-up transformer to raise the voltage up to a high level for long distance transmission. You have long distance transmission network. That line, the transmission network ends at a substation near where you live. Voltage is reduced, drops down, puts the voltage, the current is then, power is put on a local distribution line, and that comes to your house or building. That's going on for 100 plus years. We know that. What is new? If I look at the bottom half of my screen, I have new stuff. I have a solar panel, I have a storage battery, I have an electric vehicle, I have a wind turbine, I have a two-way communication. Because if I'm selling power to the electric utility from my home, they have to know how much I'm selling. Because if I'm selling too much, more than the line requires, voltage goes up. That's not good for the system. So that's why we need two-way communication. Then today we have smart inverters, which can clip the amount of power I can sell to the distribution network if voltage is too high. That's why I need two-way communication. All that is happening, that is the reality today. Solar, storage battery, electric vehicles, wind turbines, in addition to the nuclear plant and coal plant and all the other stuff. So as we build more and more solar, we cannot shut down everything else. It's not going to happen. But it's still building nuclear plants, still building coal plants, still building gas-fired power plants. Those will stay for, 20 years or more. So this is the context I'm talking. Solar will go up, but it would live with other source of generation at least next 20, 30 years. Okay, now, what is the physical shape of a smart grid? This is a physical shape. I say we'll have in the near future, maybe next 5 to 10 years, an interconnected microgrids which are intelligent. What's a microgrid? It is, as the name suggests, a small part of a grid which is serving a small community. Like you see here, I got 1, 2, 3, 4 microgrids on my screen. One on the top, center of the screen on the top, I have 4 homes with rooftop solar, and one house or home has an electric vehicle. Could be 10 of them, 20 of them. What is the distinctive feature? Feature is this microgrid has a functioning telecommunication network. You see things like a modem. That will make sure that all the homes are properly served from utility power. If not, local generation, that's done. One on the right-hand side on the top of the screen is also a second microgrid, which has some other sources like battery sources. The one in the middle is a bigger microgrid, which has connection to the transformer from the power company. It is connected to the transformer from the wind turbine. It has a battery storage, all that together. Why I say interconnected microgrid? Every microgrid by design has some local generation to meet their own needs. Some, not 100%. If there's some shortage, maybe it's a cloudy day, your rooftop solar is not enough to serve the load, then some other microgrid, which has connection to the power company's grid, can bring extra power to feed your microgrid such that the loss or shortage of power caused by cloudy weather would not turn things dark for you. That's why I say intelligent, because they can talk to each other in real time, keep track of the reality, and they're interconnected. So before we get the whole world in a smart grid, we'll see many such interconnected microgrids, which would let us know how the things work. And that's what I'll focus on as I go down through my list of slides. So what happens then in a smart grid? We have talked about power flow so far. Power starts at the power station, step-up transformer, transmission line, distribution substation, step-down transformer comes to my house. We know that. What is new, we are now superimposing on this power network an information network. So this is my power network. We all know this. I just said that, right? Power plant, step-up transformer, long-distance transmission line, receiving station, distribution substation, local feeder network, then your buildings, your home, your factory, your office building, your local generation could be flywheel, could be a gas turbine, all of that is happening today. On top of this, I'm superimposing what I call a information infrastructure, the red lines. This is new. This is the reason why you call a grid a smart grid. Okay, you notice something new here. What is new? This information infrastructure has red arrows going both ways. That is new, up and down. That means you must have ability to transfer information both ways. The power company sends a signal that they will drop the voltage for something. What can I do? I get that command. I write back to the power company, I can accept 5% voltage drop, not 10%, because I have some sensitive equipment at home that cannot operate unless voltage is in plus minus 5% range. That's all automatic. That's the added value of the smart grid. That's the definition. Now, what are the issues we are facing today in deploying smart grid? The many different kinds of issues. Number one, regulatory issues, meaning laws and regulations. Business is money, buying and selling, technical issues, and privacy security issues. This is a very interesting and important element because people ask me, if I want to put things on the internet to exchange power, what happens if somebody hacks that and turns my lights off? It's possible. So what are we doing to address that concern? I'll talk about that. Okay, now let's talk about issues related to regulations. We have to have time varying rates to incentivize the customer to use less power during peak hours. But the question comes back, my second bullet, who pays the upfront cost? A normal power meter costs about $20 in that range. A smart meter with the associated telecom network costs $200. Who pays that $200? Is it me as a customer, power company, government? Those have to be discussed, and they are being discussed globally now. Many countries are doing this. Very crucial issue, who owns the data? Power company in my house is a smart grid. They monitor my power real time, and collect data. And they publish the data on the internet every 30 minutes. So I can go to the internet, see what I consumed in the last 24 hours every half an hour. I have the data, I can get that. But do I own that data? Our power company owns that data. By owning means, can they sell it to somebody to figure out what kind of people live in this neighborhood, how much power they use at 4 a.m. and 4 p.m.? That would be a good marketing resource for them to sell to people. Those decisions have not been made yet. This is a big issue in Europe right now. Who owns the data? So those are issues for regulations. You're not a lawyer, I know that, so you don't care, but you must know this will come up when you work as an engineer or researcher down the road. That's regulation. Second, business issues, return on the investment. Power company in the US are regulated. They are given some guaranteed return on their investment. So now they're investing extra few $100 million to put the smart meters in their customers' homes. So what is the return on the investment? We have to ask that question. Again, we are the ratepayers. We pay the bill end of the month, but who takes the responsibility? If it is too much money for me as a homeowner to receive a smart meter because I have to pay for it for the next 2 years, I may not accept it. Then what happens? Very important part for deployment, trained manpower. We need people who know communication very well to maintain the telecom network. We know people who have to go and install the smart meter, which is not the same as a digital meter, and take the data out of it. Those are issues I'm not talking about. That's not my business, but I want to show if you want to have the big, comprehensive smart grid picture, you must be aware of this issue, regulation, business, technology, and so on. Fine. So let's talk about security issues first. Also privacy issues. As I said before, right? The smart grid starts at the generator, ends at the refrigerator. Does that mean the power company can scan my demand in a very few seconds and figure out when I open the fridge door, how long the fridge motor runs, is the light on, light off? If they know all that, they know my private life. They can tell when I turn my hair dryer on, when I turn my tea kettle on, when I turn the toaster on, all of the issues. Those are privacy issues. Who owns the data? This has not been solved yet. This is talked about. Then the question is data transmission over the public internet. What does it mean? As I said to you already, that my house has a smart meter. How does the data from my smart meter goes to the power company control center? Here how it works. My smart meter transmits the reading for my meter in real time to a microwave network. Okay, that microwave network is built by the power company. That network sends data to a data concentrator, which is looking at data from maybe 100 homes, 100 houses. That data concentrator is talking to the substation using the GPRS mobile phone network. That network is run by the phone company. Power company pays a monthly fee to use that. When the data reaches the substation, from the substation, it goes to the control center of the company over their own fiber network. That's the own network. That means part of the data has been transferred through the open internet GPRS network. Security issues come up. We'll talk about that later on. Then the issue is bullet number 2, data sharing by multiple parties. So this is microwave network first, GPRS. Then you have last leg, which is your fiber optic line. So many people are involved in this. So who owns the data? These are issues we can talk about later on. Now, this is my focus now, technical issues. 6 issues. I'll focus more on the bottom 3, which are in red letters. First of all, service, monitoring, and recovery. Before the smart grid, when I lost power in my house, power company doesn't know how I lost power. Now they know, because even though there's no power, my meter is transmitting data over a microwave network, not the power line. Now keep that in mind, microwave network, not the power line. So then microwave network is not down because that's a separate network. That gets data to the data concentrator, which is using the phone network, GPRS, to send data to the substation. That's how they know that my house has no power. They can work on that, number 1. Number two, remote meter reading and billing, of course, because they don't have to come to my house to read my meter. My meter is broadcasting data in real time. They can read it, put the bill, and send the bill to my internet account. Number three, very important, transformer and switchgear loading. Sometimes on a hot summer day, the local transformer serving few homes and buildings can get overloaded. Before my smart grid, they have no way it's happening. They could guess. Now, because of smart grid, they have real-time data and figure this out. Those are the things happening in the background. Now, what is my focus? First three are happening. Lower three are what I can do. I can use smart grid to reduce my peak load. I'll show you how. I can use my smart grid to add more solar PV more effectively. I can also use smart grid to control my customers' demand in real time to reduce peak load. Those are my actions. I'll take one at a time. Let's look at the electrical load profile in Virginia, USA, where I live. Annual load profile showing what percentage of the time I have how much load. If you follow this line here, about 7,000 megawatt of load is there all the time, 24/7. Next 2,000, 3,000 is there half the time. The last 3,000 megawatt is there only 5% of the time, 5% of the time. That means few hours in a year. That's how the system works. That's Virginia, Saudi Arabia, even more severe case. Saudi Arabia data from 2016, peak load for the whole year of 2016 was 66,131 megawatts. Last 5%, meaning about 2,500 megawatt, 3,500 megawatt, 62.8 and 66, happens only 5% of the time. That means if you can somehow avoid that last 5%, you don't need 3,000 megawatts of extra generation. It's a lot of money, a lot of money. So how can we use smart grid to avoid the last 3,000 megawatt, which happens only a few hours in a year? That's the challenge for engineers, and we'll see how we can make it work. I'm going to show you some examples from different countries. See what is happening here. You saw the US number. The highest 20% of the load, highest 20% happens only 5% of the time. 5%, highest 20%. US. Australia, even more severe. The highest 15% happens only 1% of the time. So if you can avoid that 1%, you can save a lot of capacity. Don't need it. Egypt, I've worked there quite a bit. Same data, highest 15% happens only 1% of the time. Saudi Arabia, interesting. Highest 5% happens only 3/4%, not even 1%. So if you can do something to avoid that 3/4%, you can save about 3,500 megawatts. There's a lot of money being spent just for that one small amount of time. No industry in the world does it except power industry. Can you imagine an airline is keeping 20% airplanes on the ground in case people show up, right? That doesn't happen. People show up, they say, go on the next flight, go now. So we don't want to say go next flight in power system, but we can do something with it. That's my next few slides. Okay, that's the issue of demand response, system control. Now we have other component, which is renewables. This is how is today's market looking like. More wind, rooftop solar, electric vehicles. Fine. This is your campus, Chaos. I was there maybe 8-9 years ago. It was looking like this, very nice and clean. It's a 2 megawatt. At the time, is the highest rooftop solar project in the world. 2 megawatt Chaos campus. Very good. But this is new. When thing gets old, it looks different. This is over time, that's what happens. You have dust, you have sandstorm. They build up on the solar panel. They don't look like this all the time. They look like this quite a bit of the time. Then what you do? I have seen, in fact, at Chaos and some Saudi locations, because of not washing the panel on a regular basis, you lose 15, 20% of capacity. 20% capacity is lost because of dust on the panel. On the right-hand side of my screen, again, saw the picture, partly washed, and it's better. But washing takes money and time. So this is an example from Riyadh, Saudi Arabia. I have data from a 100 kilowatt PV system in Riyadh, Saudi Arabia. Look at two data sets. In September, it reached almost 100 kilowatt every day, 190 kilowatt every day, September. And it was clean, no sandstorm. When I go to sandstorm season, July, for some reason, the output is half. That means two things. With sandstorm, the sky not clear, of course, and then more sand on the solar panel. That's the challenge. How can you fix it? And we'll get to that in a few minutes. So this is the challenge. Now, this is an example of how to clean the solar panel. This is a Saudi project again. And here we have a machine which has some water in it and cleaning the panel as it goes. It's possible, but it needs two things. It needs the machine, it needs money, it needs water. So that's the challenge. Okay, so the question is, how can the smart grid help in this situation? We know solar, Saudi Arabia is very sunny. You get sun all the time, but you also have storms, desert sandstorms. That's why you have this situation that we have to be aware of. We can't just say Saudi Arabia is sunny and bring solar all the time. It's not going to work. This is the challenge you face. Anyway, so this is the challenge I have to figure it out as an engineer. How can I adjust my load to make sure supply is limited? I can handle it. That's what we call short-term load control for large number of devices through demand response. That's my target. What is demand response? It's a customer action to control load to meet a certain target. What is the target? I know sandstorm coming. I know I'll lose my solar capacity 10, 15%. I have that notification in advance. I can send signals to my customers and tell them, can you please not run your washing machine? Can you please turn down the air conditioner? This and that. That's request. I'll show an example of how we can do that automatically. Good. I have a project, I did that at Virginia Tech. This is selective control of appliances under the signal from the power company because of supply shortage. Two things, I have this air conditioner, water heater, clothes dryer, I call HEM, which stands for Home Energy Management Unit, and the load controller box and my power supply. This is my breaker box. Hook it up. When I get a signal, I need to drop my capacity, my demand by 10%. I have a schedule. Which one goes first? Do I turn the AC off? No. Turn it down a little bit, raise the temperature. I may not heat the water at the time. I may not dry my clothes. I may not charge the electric vehicle. Those are done all automatically. Now, what is the issue of IoT-based building automation system? We know that in Saudi Arabia, rooftop solar is gaining popularity. We see that, right? I know the rooftop solar can help mitigating peak loads. You have Chaos Campus rooftop solar. When the load is high afternoon, it's also sunny. That means your solar PV is doing well. So that means you don't need to buy as much power from the power company. That's mitigating peak load. But how do you control load inside the building? That's called building automation system, which helps to maintain a comfortable, healthy indoor environment. I'll give an example in a minute. But for that to happen, we need to have low-cost building automation systems that can be easily deployed. My lab at Virginia Tech, this is a low-cost building automation system. You can see we have different kinds of thermostats on the left-hand side. We have the controller for air conditioning, rooftop unit, different kinds of light bulbs, light switch, smart light switch, lighting load controller, dimmer ballast, smart plug, different kinds of smart plug, occupancy sensor, light sensor, power meter. All of these are talking to a literally iPhone or iPad to control. I also monitor the rooftop solar on my building rooftop. If you want to know more about this as a researcher, go to the website bmos.org, the left side of the screen at the bottom, bemoss.org, which has some examples, some software you can download, and my publications as well. Other website is bemcontrols.com. It's a company in Virginia which has deployed these solutions and has some case studies. Look at that at your leisure. If you want to talk to somebody in the company, the email you can write to them and get a discussion going. So some examples I give you now. Examples. This is a classroom in one of my buildings. I put my BMOS software here. What do I have here? Sensor for carbon dioxide, noise, temperature, humidity. One sensor does all of that. It's a Wi-Fi sensor. I have a smart plug load controller to control the room, printer, LED screen, all that. Motion sensor, nobody in the classroom. I turn the lights off, turn the AC down. Thermostat to monitor this. This is my setup, real world setup. And rooftop, I have a air conditioner, of course, and a power meter to make sure when I do the control, I can show that I'm saving electricity. Okay, this is the data from my classroom here. You see, this is a iPad screen capture. You see here temperature, humidity, pressure, CO2, noise, outdoor temperature, all the data is there. And also the blue screen shows you the CO2 concentration changing as the class sets in place. Students come in, they breathe, and the room has no window, you can tell here, CO2 goes up. And how do I control that CO2 level? This is my challenge. Okay, second example, how I can control lighting in an office building to reduce peak load and energy. This is an office building in Virginia, 5,000 square feet. I have 3 lighting controllers, 1 power meter. You can see the middle part of this picture here is a working area, skylight, and the ceiling lights. This is interesting. I go there and say, what's going on? You have so much sun coming down from the skylight, why keep the lights on? The answer is, if you turn the lights off, people will think we lost electricity. They don't want to do that. They have no opportunity to dim the lights before we put the experiment. Now they can dim the lights when sunlight is strong. It's done automatically. The lower right-hand side is a conference room. Nobody's there. Every light is on. That's normal practice. Now with our control system, nobody in the room, light is dimmed, not fully off. The upper right-hand side picture shows a work area for staff. They're going to lunch. In this case, light is on full capacity. Don't have to. We have the control system now to dim the lights. As a result, if you see the screen at the bottom of my screen here, how much do they save? This real data that I measured as a result of scheduling and dimming. That's it. Don't turn the lights off. So you see about 34-35% savings of energy by doing this. That's the IoT applications. Third example is battery. Our bmos.org, our control system that we built, can also monitor battery operation. It's a 5 kilowatt battery in our building going on. Again, people say if you put a battery, does it take space? It does not. This is the garage where you put the battery. We hung the battery on the wall of the garage. So no parking spot was lost as a result. It can be done. This is my building at Virginia Tech. This is about 9 years old. And this is, we have no sandstorm, it's pretty clean. But my point is this rooftop solar can be also controlled by the building automation system right here. So now I talk about one building each at a time so far. Now talk about a campus, like KAUST campus. What we have done at Virginia Tech is put all my algorithm, my data in the cloud. It's AWS cloud. Each building has heating, cooling, lighting load, plug load, sensor, water meter, PV, security camera, everybody. Each building has an account in the cloud, and that data is shared among buildings. And then on the upper middle part of the screen, I have this computer picture here. This is the system control manager. They can see remotely what every building is doing in real time. and then take action based on if one building has less rooftop solar capacity because of cloudy weather, because of dust, they can rearrange the power supply between buildings to make sure you don't create an extra peak for the power company, which has higher cost because of the peak load situation. This is happening. So I can do. Also, other thing is, I say occupant comfort, very important. If you have too much CO2 in a building, then what happens? You have uncomfortable condition in the building. So we monitor CO2, we detect high concentration, we throw more fresh air to reduce the CO2 level. That's how we guarantee occupant comfort, and many other things. Alarm notification, security, building energy management, all of that can be done. You can go to the bmos.org website, look at my publications, and see how we have done it. That would be the best way to go forward. So, kind of finishing up now. Now, I hope you understood last 40 minutes, things are changing. We call it new paradigm for the power system, new paradigm. Why new paradigm? Because it is not only one source power company sending power to me, it is many people sending power from rooftop solar. So historically, we call it demand-driven supply. We forecast demand and build power plants to supply the demand. That's called supply responding to demand. That's going on. Today, new reality is supply-driven demand. Why supply is now unknown, right? You don't know cloud will be there tomorrow afternoon. Supply could change. So demand has to be adjusted to make sure I can live with the supply. Otherwise, I'll be in the dark. So this is where, as you can tell now, the demand response idea comes about and makes the demand now interdependent on supply. Interesting concept. We call it the smart grid ecosystem. And this is how it looks like, the smart grid ecosystem, where you have the yellow circle, smart building, could be building at KAUST. Then you got a KAUST campus, smart campus, which would be look like this, control. We have done that work, it's possible. Then you have smart city, like many campuses, many shopping centers, many corporate headquarters could be put together in a smart city. And then many smart cities can be fed by a smart grid, which could be South Electric Company smart grid. So again, the new thing is, if you read the bottom part of the screen here, I must support this by information and communication technology, ICT, distributed network of sensors, data centers, and clouds. All that put together gives me the smart grid ecosystem. So this is my last slide. Thank you very much. I think my time is right, 45 minutes. And I am now ready for Shihab to do the Q&A.
Thank you. Thank you very much, Professor Saifur Rahman, for the very inspiring talk. We have actually a good set of questions from the audience that I would like to share with you. So the first one, the audience asks, who should be responsible for the investment necessary to transit traditional grids to smart grids? Is it the government, the power distribution companies, or the clients?
End of the day is us, client, end of the day. But not in the beginning. In Virginia, what happens? The power company invests, but they collect it from me and you over time. So, but for them to collect from me, I must give them permission to collect from me. And that is done by regulators. So power company goes to the regulator. It costs power company X $500 million over 3 years to put smart meter on everybody's house. They put that number. The regulators discuss it, talk about it. People like me can go and testify, I don't like it, I like it, whatever it is. Then they give a number. Okay, you will get 300 or 500, $300 million over 3 years to do this. They borrow money from the bank. They borrow money, put it together, and then every month they add that cost to electric bill. And then I don't mind, I pay extra $5 a month, not a big deal. So I say, okay, go ahead, do that. That's how it is done in the US.
Maybe I can add an additional sort of question to this that is related. So in the US now, there's, and maybe in Europe as well, there's the business model of an aggregator has emerged. It's tightly connected to this question. So can you shed some light on the aggregator business model and maybe some examples of how that works or how it has worked in certain cases?
Aggregator is a good question. As I talked about this demand response program, I can save 5 kilowatts, 10 kilowatts from my house. For a power company to keep track of million customers, 5 kilowatt each is a lot of work. They don't do that. They'll say to an aggregator, talk to 100 homes and take 10 kilowatt from each house is their headache, aggregator headache. 10 times 100 is 1,000. That's 1 megawatt. That number is useful for the power company. 5 kilowatt is noise for them. So aggregator gets some money from the power company to talk to me and set up the network. They will manage my home component, home control centers, so that if something goes bad, they'll send a technician to fix it. Power company doesn't take this headache. My company, Dominion Energy in Virginia, has more than 2 million customers, 2 million. They cannot have 2 million accounts to fix things. They cannot. So aggregator is the middleman. Talk about this. They say, okay, I, aggregator A, can have 100 homes or 100 commercial buildings. Each can save 100 kilowatts. That's 10 megawatts. They will sell that 10 megawatt capacity savings to the power company, get some money, and they will arrange between these 100 buildings how to adjust it. That's the job of aggregator. Thank you, Shihab.
Thank you. You're welcome. So I have another question. So in the lack of when we lack time of use tariffs for power prices, how can the smart grid sort of be beneficial in such a scenario? When we specifically discuss demand response and demand side management, etc. How can we make use of the smart grid in this case?
Well, yeah, demand response activities in the US are by choice, not by requirement, by choice. Give somebody a choice, they must be getting some incentive, otherwise they will not do it. That's the pricing structure, by choice. However, in some countries, in some parts of the US even, it's not by choice. That because if the power company is required to buy extra capacity, gas turbines to meet the peak load on a very hot summer day, that cost of the extra capacity has to be, end of the day, paid by the consumer, end of the day. So the regulator will say, consumers' price will go up because power company has to buy the extra generator. Rather than buying and raising everybody's power bill, let's put some restrictions that from 3 to 5 p.m., you would not be allowed to use as much power, your voltage will be dropped. This is not a by choice, by requirement. Then it works. But in the US, the way the culture is, it's more incentive-based. So answer to your question is, if you don't have the rate structure to incentivize, power company can do that by changing voltage. They can do that. Other benefit of a smart grid is the following. This is more important for the power company. Power company does what they call dynamic voltage regulation, DVR. What is it? You know, those are power engineers in the audience. Power loss is V squared over R. Higher the V, higher the loss. And loss is a loss for the power, not me, power company's loss, because they are not getting paid for this. So they do dynamically change the voltage so that their loss goes down and they lose less revenue. That's their objective. They do this all the time, all over the world, DVR. The problem is, if they drop the voltage too much, the loss goes down, but people complain. In the US, the law is voltage can be dropped by no more than 5%. That's a law. But they don't know with our smart meter what is the voltage in the end of the feeder. They have no idea. They make a guess. Sometimes they fail, sometimes they don't work out. Now, smart meter, that's their meter. They know exactly the voltage at every house. Knowing that information, they can decide the bigger range of voltage control. That's their benefit. This is the main reason why smart meters are taking a lot of application in the US, because that reason.
Great. If we shift to the consumer now and ask some questions there. So, the lack of consumer awareness about the issues in the power sector is one of the main challenges in the smart grid implementation. Do you have any suggestions to overcome this challenge? And in light of that, how do we encourage consumers to install PV?
Well, first one first. Awareness is, for me as an educator, very important. If people don't know, they don't care. So, in fact, when in the US 10 years ago, almost 10 years ago now, when the smart meter becoming more popular, government spent more than $100 million educating customers, TV ad, school programs, what it is. That's requirement. That has to be done everywhere. I've seen in other countries, I've seen Egypt, seen in Bangladesh, TV ad about the benefit of smart meters. So it can be done. So that is happening. But the other question is, the second part is, can you repeat that, please?
It's how do you encourage consumers? They lack the knowledge, but how do you then encourage them to install PV or other smart grid related technologies?
Well, PV is one, other technology different. Let's talk about PV first. PV in the US, in Germany, I know, for even India, Thailand, China, if you put PV on your rooftop, you get some government incentive through tax or through other cash incentive. That's how PV is done. Hawaii has so much strong incentive that during the afternoon hours, the PV is producing more power than the all demand put together. Power company has no need at 3 p.m. on a day. No need. This is happened because of the incentives. So unless you have some incentive to encourage people saving money by putting PV, they would not do it. So answer is very simple. Government incentive. One is cash. One is called feed-in tariff. That means if you produce PV at afternoon time, you get more money than you are spending from the power company's power that you are buying. Germany, for example, a few years ago, the feed-in tariff was 3 times. That means if you buy from power company 15 euro cents, if you sell the same kilowatt hour, you get 45 euro cents. That's how they went to the bank and borrowed money, put the solar, and they made money for the bank loan to be repaid.
Next question. It's about sensors. So, sensors are at the core of getting this smart grid system up and running. And the reliability of such sensors is an important issue. So can you shed some light on the reliability of such sensors and their operation in the power system flawlessly for years and years?
Yes, sensors have limited lifetime, that is true. And sensors are key component of this whole data collection system. What we have done, we always have redundant sensors, always, at least 2. And they're cost few dollars, not a big deal. So we have redundant sensors, and our network has enough extra capacity left to add more sensors. Then what we do, we add, and one sensor failure can be taken care of by a second sensor running in parallel. So when the first sensor fails, we get a signal to the operator. The first sensor has failed, second sensor working fine, so schedule replacement for the first sensor, and they do that. In those cases, the labor cost is higher than the sensor cost, but this is something, I am running these things for 5-6 years now in my lab. None of them have failed. None of them has failed. They can. We always have one backup always there for us to guarantee secure supply.
Okay, moving from sensors to the network. So today's industrial network protocols that are used in smart grids, how secure are such protocols today? What is sort of the latest issues that challenge such security of such networks, and is there an easy interoperability sort of mechanism to allow, legacy systems to interface with new systems, etc.?
Well, the new thing is communication. Other thing is no changes. Communication. So communication is two-way. When the power company is reading my meter and only reading, not controlling anything, then that is hacked. What will happen? The power company will get no data from me for some time. And for billing purposes, if they lose data for a day, it doesn't matter. They bill once a year, once a month. So that's not an issue. The issue is control signals. When they send a signal to turn my air conditioner down or tell me to turn the AC off. So this is where risk is there. Suppose somebody takes hold of that signal and changes the command. They turn the AC off, not down. A command was turn the electric vehicle charging off, which doesn't matter. The command was changed to turn the AC off. That's something we have to be carefully dealing with, but that has not been, it's not done. The work is still ongoing, how to do this. Because some double check. When you send a signal that turn the AC off, you'll send a signal back. Do you really mean this? Or something is wrong. So that work is machine learning, still ongoing. It's not done yet.
Okay. Would you like to shed some light on applications where batteries have made a difference? So, for example, in the Virginia load, in the load profiles that you talked about, the peak load profiles, I think that's an area of interest for the battery manufacturers, and perhaps the example in Australia is a good example. I don't know if you can shed some more light on how to tackle this 3,000 megawatts that you were mentioning. Different technologies that allow that to happen, and some success stories, for example?
Yes, in the US, many power companies have incentives. I know one in Chicago has that. If you put you mean a third party, puts a battery plant, 2 megawatt hour battery plant in downtown area, because no smell, no noise, no sound, it's no problem to put on in the parking garage also. Then the power company will buy electricity from the battery project at a price which is cheaper than them, power company running a gas turbine, for example. That's one reason. Other reason is pollution, the issue of carbon emission. As you have probably some of you know, with the Paris Climate Accord and all that, the carbon emission will have a price now. So rather than the power company paying the penalty for carbon emission and running a generator, cheaper for them to get the power for 2-3 hours on a hot summer afternoon from a battery project. That is taking over slowly, not as fast. And the reason it is slow because of the investment issues, but as the price of battery has come down significantly, I'll see that is happening more and more. One other example, Tesla, which is a car company, sells a battery package called Tesla Wall. You buy the battery package, maybe typically 5-10 kilowatt range, put on a wall, and then you can use that to run your home part of the time if the California especially has high price during peak hours. So that's an example of customer-based battery plant. Third example in Hawaii, this is happening today. If you have so much solar that is more than you need, but you need power at night or a rainy day, so that power company will be backing you up. Because the power company is selling less electricity now, they are charging very high price to back it up, very high price. The customers in Hawaii have figured out they can buy a battery cheaper than paying the extra money to the power company. They are going totally off grid. Battery is here, solar is here, the wall, Tesla wall, and I am independent. That's another example of how battery technology is helping to popularize solar PV application.
Well, thank you very much, Professor Saifur Rahman. I think we've come to the end of our questions. Again, we'd like to thank you for sharing this talk with us as part of the Winter Enrichment Program at KAUST. Again, it's virtual this year, so we can share KAUST with the world, but hopefully we get a chance for you and others to visit our campus, which is really one of the reasons we share and have created web over the years, and it has been successful. But again, this year we're able to, unfortunate, to be able to share it with the rest of the world. Yeah. So thank you very much. We appreciate your time and sharing the wisdom, and we hope to meet someday in person soon.
Thank you, Shia, very much. And the audience, I enjoyed the questions. I hope the lecture was meaningful to you. And I will be happy if you have any comments down the road. Shia, you know my email address. Let me know.
Sure.
Thank you very much.
Thank you. Thank you very much.
Okay. Bye-bye.
Bye.